Hi guys. So this tutorial is going to be a quick revision of predicate logic for your final exam, right? So the first thing we need to talk about is why do we need predicate logic? Or in other words, what is the difference between propositional logic and predicate logic? So I'll illustrate this idea with an example, right? Consider the statement, all students are intelligent, right? Let's try to translate this statement into symbolic form. If we were to use propositional logic, which of course deals with proposition, which are declarative statements that can be either true or false, then we need to come up with simple or atomic statements to represent all students are intelligent, right? So in its simplest form, maybe we'll let P be the statement. Dale is a student. And we can let Q be the statement. Dale is intelligent. And we may try to write something like P implies Q, which is if Dale is a student, then he is intelligent. Now, the problem with doing this, we cannot represent that word all because propositional logic works for this particular variable here, whereas the statement that we need to represent has that word all. So to deal with this, we introduce predicate logic, which deals with predicates. And these are, you can think of them like function, which take one or more variable and output a true or false value. Right, so we're dealing with functions, so we could define our domain to be the set of all people, and we could take a member of the domain, X, where X is a person. Then we could define S of X to be X is a student. And we could define I of X to be X is intelligent. And now, in symbolic form, we could say all students are intelligent. So what this example shows is that we need a predicate logic to quantify a statement. And one advantage is that we can define variables and relationships between variables very explicitly. So now that we know why we need predicate logic, we can talk a little bit on how to symbolize these statements. So consider this example. Some teachers are funny. This word some here is the word that we need to quantify. Teachers will be represented by one of our predicate functions. R requires a logical operator, and funny is another predicate function. Now I keep using this word function. And as we know, anytime you have a function, you also have to have a domain. So we need to define some variables to attach to these functions. So if we define our domain as a set of all people, we could say let X be a person, let T of X be X is a teacher, and let F of X be X is funny. Now to quantify the word some, we use this symbol here. So we say some people who are teachers are also funny. Or in other words, some teachers are funny. So the fancy symbols that we use are called quantifiers. And there are two quantifiers you need to know. We have the upside down A, which represents all or any or no. And we have the back to front E, which represents some or there exists. We defined our variables, which is simply the thing that you are talking about. Just the member of the domain. We also talked about using predicate function, which is just our way of defining a statement. And of course, we had our logical operators, which we borrow from propositional logic. We have and, we have or, and we have implies. And later on, you'll see we also have negate. So let's go over some examples to bring the concept home. So in this example, of course, we are dealing with some people, we'll call those X. We need to find a way to quantify this. The way we quantify everybody is using the upside down A. So for all, or for any, or for everybody, this is called the universal quantifier. We need a function for mother, and we need a function for father. We, of course, need to define our domain. We let X be a person. And now we define the mother function. So you may be inclined to say, let m of x be x has a mother. And similarly, let f of x be x has a father. Then this would give us, for all x, x has a mother and a father. And whilst this is technically correct, one of the pros of predicate logic is that we can get very specific. So, show that x has a mother who is different from the father. So let x be a person. We could define the function m as m of xy is y is the mother of x. And similarly, we could say let f of xz be that z is the father of x. So now we could write the statement as for all persons x, there exists a unique person y such that y is the mother of x, and there exists a unique person z such that z is the father of x. And this is our answer. So let's look at another example now, and let's go the other way. So now we're going to go from symbols to words. So this quantifier here we know means all. We define this function as x is a car, so this is cars. And of course, this is wheels. And this operator will be have, because that's the word that fits most sound in terms of everyday English, right? What we're doing is saying that anytime I'm a car, I also have wheels. In other words, all cars have wheels. Let's look at one more example. So in this question, we need to represent the statement there exists x such that q of x in word. And as we know, this quantifier is represented by the word some, or there exists. Now q of x is the statement that x squared plus 1 is even. So to say that there exists x, we are trying to say there exists an odd integer x such that x squared plus 1 is even. By the way, is this statement true? Is there an odd integer such that that integer squared plus 1 is even? Yes, the statement is true. So now I briefly want to discuss the difference between the universal, which is the upside down A, and the existential, which is the back to front E. What is the difference between these two quantifiers? Let me show you with some examples. Consider this first statement. There exists x and there exists y such that x plus y is equal to 0. What does this statement mean? It means that there are some values of x and some values of y satisfying x plus y is equal to 0. And of course, we could easily check that. Maybe we have a value of x as 1, and then maybe we have the value of y as minus 1. So it is true to say that for some values of x and some values of y, x plus y is equal to 0. In fact, we could write this as there exists xy such that x plus y is 0. This next statement For all x and all y, x plus y is 0. Or for all x, y, x plus y is 0. What does this statement mean? It means for any choice of x and any choice of y satisfies x plus y is 0. Now, is this true? Well, let's see. For any choice of x, okay, maybe we choose x is 2. And any choice of y, okay, we can choose y is 3. Ah, this is not equal to 0. But this is a false statement. And why is it false? Because we cannot choose any value of x and any value of y to satisfy this statement. In this third example, we have for all x, there exists y such that x plus y is equal to 0. This means for any choice in x, there's a corresponding value of y which satisfies x plus y is equal to 0. Is this statement true? Well, let's see. If we choose x is 2, then there is a corresponding value that gives us 0. If x is a half, there's still a corresponding value to give us 0. If x is negative 1, we still have a corresponding value to give us 0. So this statement is true because for any value of x that we choose, we could find a specific value of y corresponding to that value of x to make the statement true. In this last one, we have there exists x such that for all y, x plus y is equal to 0. This means that there's a value of x such that all values of y satisfy the statement x plus y is equal to 0. Now, is this true? Well, let's see. If there exists a value of x, we could choose and fix a value of x. Let's say we choose 7. For this value 7, all choices of y, all possible choices of y, must make this statement go to 0. So let's take minus 2. No, that does not give us 0. Let's take 3. That doesn't give us 0 either. Let's take minus 7. That gives us 0. Let's take 1. That does not give us 0. So even though there is a value of y which makes this true, not all values of y make the statement true. Hence, the statement is false. So the last thing that I want to talk about is how to negate quantifier. So when we say the word negation of a statement, what we are talking about is denial of that statement. And that means we want the statement to return the opposite truth value. So for example, in propositional logic, if we had a statement P, Kiran is a boy, which is of course true, and we negated the statement, we would get Kiran is not a boy, which is of course false. So we see here that the negation of the statement returns the opposite truth value as the original statement. So let's look at negation in terms of predicate logic now. Consider these circles and the statement, some of these circles are shaded. That is, of course, a true statement. So intuitively, if you wanted to negate this statement, you may say, some of these circles are not shaded. But this is not correct. And the reason this is not correct is because some of these circles are in fact not shaded, which means this is a true statement. When we are negating a statement, we want our negated statement to output the opposite truth value. So we need to come up with a statement that is false. And the way we do that is by saying all of these circles are not shaded. That is, of course, false because there are some circles that are shaded. Another way we could say that is that no circle is shaded, which is, of course, a false statement because we have circles that are shaded. So in symbol notation, if we want to negate the statement for all x, p of x, we will get there exists x, which is not p of x. And if we wanted to negate there exists x, p of x, we get for all x, not P of X. So let's look at another example. Some of my students attend class. This is, of course, a true statement. For this example, I'm going to convert this statement into symbolic form. So we could let X be a person, let S of X represent X is a student, and let A of X be X attends class. Then our statement is some of, or there exists, some of my students attend class. So we want to negate this statement. Using our rules, we'll get all. And in words, we could say none of my students attend class. Of course, that's a false statement, so we've successfully negated the original statement. We could also use De Morgan's law for negation to get, and in words, this would be all of my students do not attend class, which of course is again false. So these are two ways that you can negate a predicate statement. If you negate the existential quantifier, you could use the word all, or you could use the word none. So this was a very crude crash course for predicate logic, but hopefully it gets the idea down. This more uncovers what will actually be tested on your final exam. So hopefully that's good enough. Of course, if there are any questions, you could email me or you could send a message on the WhatsApp group. Okay, bye.